Good day and welcome to today's class. So we want to talk about a concept under the calculus, which is known as mean value theorem. When we say mean value theorem under the study of calculus, it is a concept where finding the slope of a function, okay, at a specified point in a given interval. Okay, so before the advent of this mean value theorem, there was a concept or theorem that was used to discuss this mean value theorem. The theorem is known as the Rolle's theorem. Okay, this theorem was first published by a French mathematician called Rolle in the 17th century. Okay, and he measures of a function defined in a given interval and try to uh, look at the slope of that function at a specified point. Okay, at this point, we get a slope uh, of that function which is parallel to the horizontal axis. Okay, so let's quickly look at the Rolle's theorem and how it's related to the mean value theorem. Okay, so it says let f of x be a single value function which has the following properties. Okay, number one is that f of x is continuous in the closed interval AB, where A is the lower limit of the interval and B is the upper limit of the interval. And of course, when we say interval of this form, it means an interval that is a subset of the real number R. Okay, so two, f of s is differentiable in the open interval AB. Okay, at least this interval, but without A and B, without the upper and the lower limit. Okay, and thirdly, the third condition says that if we compute uh, the function at A and at B, okay, such that f of A is the same as f of B. Okay, so this sentence says then there is a point, okay, there is a point C which is an intermediary point in this interval such that the slope of this function at that point is 0. Okay, so this is what the Rolle's theorem says, and let's quickly look at these or the behavior of this concept on the graph. Okay, So if you have a function whose behavior is like this, a function f of x, and this is the horizontal axis. Okay, of course, any point here uh, is a member of the real line, and also any point y here, y which is similar to f of x. Okay, it's also a number from the real line. Okay, so this curve as we have it in the theorem is defined in the interval a and b. Okay, okay, from here you see that this function is continuous everywhere. Okay, because there is no jump or a hole throughout the interval. Okay, that is, the function is defined throughout the interval. Okay, that was the first assumption. The second assumption says that without these 2 points, okay, the slope of this function is defined also in this interval. Okay, it means at any point of this interval, okay, the derivative of this function exists. And thirdly, says if you have to compute f of a, okay, and we'll compute f of b here, okay, obviously we'll see that f of a and f of b are the same. So if this happens, the theorem now says there is a point, an intermediary point C, okay, which is known as the specified point, okay, and this point is called a prescribed point of the Ross theorem, because at this point the slope f prime of C will be 0. It's 0 because it will be parallel to the x-axis. Okay, so as you can see, so this is one way, because here we'll see that f of a and f of b are the same, and of course they are equal to 0. Okay, even if they are not equal to 0, the concept still remain. Okay, so let us give you a quick graph about that. That is, if you have a line like this, where we have f of a and f of b, okay, the point here is a and the point here is b. Okay, similarly, okay, if what you have is a constant, okay, of course at a we have f of a, and at b we have f of b. We'll see that this curve was also the same here. I mean, this evaluation are the same. Okay, in this case, we can find the a specified point C at any point here. Okay, and at any point that we do that, we'll see that the slope is nothing but 0. Okay, so this is what the Richter theorem actually say. So as for the proof of this, okay, if we let's quickly say the proof of this. Okay, is defined in the interval AB, okay, and of course the three assumptions as we have said also holds. Okay, then if f of x is a constant, let's say k is a constant, okay, obviously as it is being explained on the second graph, okay, obviously we can see there is a point, okay, or there are some points, okay, because in this case it is not only just one point that the slope will become 0 in this case if k is constant as we have shown in the graph. Okay, so you can say there are some points, okay, but in order to be or in order to be constructed to be conform with the theorem, let's say there is a point C, okay, which belongs to this interval. Of course, this is obvious. This is obvious. Obvious because the function is a constant. If we differentiate this, okay, the derivative of this is 0, and at C, okay, is also 0. So this is obvious. So secondly, that is, if I have assumed the function to be this, so this is what happened. Okay, secondly, suppose f of x is defined in this interval, okay, we now see if f of x, okay, is more than f of c, okay, uh, by the Fermat's law, or the let's say this, so by the Fermat's theorem, okay, what it means is that this function has a minimum at c. So if it has a minimum at c by the Fermat theorem, okay, because if this happens, okay, it means in this case f of c is the minimum, and if that happens according to the Fermat theorem, okay, we say this is 0. In that case, we say the c is a critical point, okay, of this function, okay. And thirdly, if f of s is less than f of c for some x in AB, also by the Fermat theorem, okay, we say this function has a maximum at c, okay. And in that case, by Fermat theorem, this also is, okay. So this is how the Rose theorem is proved, okay. So as for the examples of the Rose theorem, okay, this example are numerous, but for the case of this class, we'll consider one or two examples, okay, to see how one can apply the Rose theorem. Okay. Okay, so we are given this example, and we are asked to find the prescribed point, okay, uh, by the Rose theorem if the given function is this, okay. So uh, we are given f of x to be equal to x squared minus 5x plus 4, okay, according to the hypothesis of the theorem of the Rho theorem, okay, three things must be satisfied, Okay, f of x is continuous. When I say f of x, I'm referring to this function. It's continuous throughout the interval 1 to 4. Secondly, f of x is differentiable. It means this means the derivative of this function exists, okay, throughout okay. The derivative of this function exists throughout from 1 to 4, excluding the last two limits. And thirdly, if we compute f of 1, okay, we'll see that f of 1 here is 0, and this is similar to f of 4. Okay, if you do that, we'll put 1 here. Okay, let us see this from here. So now, this means that if you have to replace C here, okay, this means this will be 2C minus 5 equals 0, according to the Ross theorem that says f prime of C is 0. Okay, and if you have to replace C here, okay, it means this slope at C becomes 0 here. Okay, so this implies that 2C minus 5 equal to 0, or 2C equal to 5, and this implies that C is 2.5. And of course, we see that this point lies between 1 and 4. Okay, so the prescribed point here is 2.5 in this interval. Okay, so if you have to see this, the graph of this is somewhat something like this, just a sketch. Okay, this is 1, this is 4. The curve is somewhere like this. Okay, and the slope is somewhere here. Okay, this is the point 2.5. Okay, and the that slope, okay, which is this curve there is at this is 2.5. Okay, the slope at 2.5 is 0. Okay, so that is what the theorem is saying here. So let us consider another example to illustrate this. Another example. So example 2. So we have to determine whether the Ross theorem is applicable to the function f of x equals. Okay, so we want to determine whether the Ross theorem is applicable to this function. Okay, so when we look at this function very well, okay, we'll see that from the first hypothesis of the Ross theorem, okay, that condition will fail. That is, this function is not continuous in this interval. Okay, this function is not continuous because at point x equal to 2, okay, this is undefined. And because of this singular reason, okay, the Ross theorem is not applicable. Okay, so let's say this. Since f of x, that is f of x, is not continuous at 2, okay, 2, which is a member of this interval, okay, then the Ross theorem, is not applicable, okay. So with this reason, okay, one should stop here, okay, it's not applicable, and then we stop because of this singularism, okay, the Ross theorem is not applicable, okay. So let's say this: since f of x, that is f of x, is not continuous at 2, okay, 2, which is a member of this interval, okay, then the Ross theorem is not applicable, okay. So with this reason, okay, one should stop here, okay, it's not applicable, and then we stop, okay. So there are a few more examples. I think let's consider one. Yeah, can I give one as exercise uh, for the okay, so just for practice. So example 3, okay, so again I want to check whether the Ross theorem is applicable to the function f of x equal to x minus square root of x, okay, in the interval 0 to 1, okay. So say solution, okay. So by the three hypotheses of the Ross theorem, okay, the Ross theorem, we want to see whether this will be satisfied. Okay, so from the first assumption, we'll see that f of x, that is the given f of x there, okay, is continuous. Okay. Everywhere in 0 to 1. Okay. Okay. I'll just repeat the point 0. Okay. This f of 0 will be defined up to or get to 1. Okay. To be defined throughout. Okay. However, let's see the second assumption, which says the derivative or the if f of x is differentiable here. Okay, before we do that, let's differentiate f of x. So if we differentiate f of x, this will be 1, and this will be minus 1 over 2 square root of x. Okay? We'll see that this function here, or derivative of this function, okay, is not differentiable at x equals 0. Okay, because if x equals 0, okay, f prime of 0 will be undefined, and because of this singular reason, okay, we say this can't hold. This can't hold. Okay, so this can't hold. Even though f of 0 is 0 and f of 1 is also 0. Even though f of 0 and f of 1 are the same. Even though we have this, okay? But for the fact that the derivative of f of x, okay, is not differentiable as 0, okay? Okay, neglect the fact that the Ross theorem will be applicable. Okay, so this is how we make use of the Ross theorem. So if the Ross theorem is applicable, that is, if the three hypotheses of the Ross theorem are satisfied, then one can now move on to find the prescribed point. That is the critical point, which is prescribed by the Ross theorem. Okay, so that is that on the Ross theorem. Okay, in our next class, we'll now look at the mean value theorem properly. But before that, let me give you one exercise. So, exercise. Find the point prescribed by the Ross theorem if f of x is equal to x squared minus 9x plus 8 all over x plus 1 in the interval, or in the interval one to 8. Okay,